So we're continuing the afternoon session with David Ben Zvi, who will speak about geometric character theory.
Thank you. I'd like to thank the organizers for what, for me, has been a really inspiring conference. And also, I wanted to thank Mike and Paula and everyone who's helped make this work. And in particular, my slides. I have the nice computer slides, and then I realized their orientation was wrong. So today I scrambled, and we went more traditional. Also, one more thing, I noticed that the page, if you haven't looked across the page, there's another talk afterwards, just to make sure Andrei Calderaro is speaking. So please remember. So I wanted to talk about joint work with David Nadler, which I'm vaguely calling geometric character theory. And this is part of an ongoing project where the general theme of the project is to understand relations between representation theory and gauge theory, maybe inspired initially by work of Kapustin and Witten and sequent works. So the ideas here, I'd like to kind of talk about outline a vague dictionary where we can think about representation theory of groups as roughly captured by gauge theory. And this is something that's emerged, I think, in the last few years, is how much of the rich inner structure of geometric representation theory is captured beautifully by gauge theory. So roughly the kind of structure I'm going to focus on is try to explain how algebraic structures in representation theory are captured. I'm just only going to look at topological field theory structures in gauge theory. And for example, I'm going to try to explain a little bit about how classical geometric constructions of representations match with, for example, with gauge sigma models. If you want to understand particular representations, particular operators on representations, this match very nicely with defects, singularities, and domain walls in the field theory. Today's main theme is going to be about taking traces or taking characters of representations, which physically will match with compactification on a circle. And the overarching goals involve the deepest problems that we might try to understand with this involve Langland's duality, which physically is captured by S duality. But today I'm going to focus on this part of dimensions, traces, and characters. So let me first say something about what do we mean by, how do we understand dimensions in topological field theory. So suppose we're starting with an n-dimensional topological quantum field theory. We're compactifying it on some n-1 manifold M. So a mathematician might think we look at the vector space as some functor attaches to M, or we might look at the Hamiltonian formalism on M cross R. And we get a vector space, which I'll just call Z of M. So this is the Hilbert space of the theory compactified on M. If we reverse the orientation of M, we're going to get some other vector space, just what the theory assigns to M opposite. So one thing we know is that there are natural relations between these two, and they're captured geometrically as follows. We use topological field theory to notice that we have this kind of right elbow, which gives us an evaluation map from the vector space attached to M, tensor the vector space attached to M up to the complex numbers. And dually, we have something I'll call co-evaluation that goes from what we assign to the empty manifold. It gives me an element of Z of M tensor Z of M up. So we have these two natural operations. And together, they satisfy what's known as the mark of Zorro, which is you go like this. And so you start with Z of M. You go to Z of M, tensor Z of M up, tensor Z of M. That's this slice. And then you go back to Z of M. And what we can do is we can straighten this out, and we get just the identity. So this tells me that this composition is supposed to be just the identity map of Z of M to itself. Now, having such a map, having these two maps, the evaluation and co-evaluation, satisfying this property, makes Z of M into something that's called a dualizable vector space, perhaps more familiar as finite dimensional. So this is saying that the Hilbert space of a topological field theory is just a finite dimensional vector space. And Z of M up is the dual. So we're going to take this picture as a notion of what do we mean by finite dimensional or dualizable, and what do we mean by dual when we get to more and more abstract contexts. In particular, if you have a finite dimensional vector space, it has a dimension. So what's the dimension? We can look at the theory on the circle. And so we're going to take the dimension of Z of M. This is the number that I get by taking Z of M cross the circle, taking the partition function of the field theory on M cross a circle. And that's what you get if you take the evaluation and the co-evaluation, compose them starting with the number 1. So it's easy to check that this is the dimension of the vector space that we all know and love. More explicitly, if you'd like, let me know if I'm off the screen. So more explicitly, what we have in the middle, Z of M tensor Z of M up, we can now identify with just matrices, just endomorphisms of this vector space. The co-evaluation map becomes identified. This is the co-evaluation map is just inclusion of the identity matrix into all matrices. The evaluation becomes the trace. A matrix on a finite dimensional vector space has a trace, and the dimension is the trace of the identity. So just spelling out dimensions of vector spaces in some gory detail. And what's the point of saying things in this detail is that we can work in, take all these ideas and take them to extended field theory. So this slide here is remarkably similar. I think it's essentially identical to one that Dan Fried had in his talk a long time ago on Monday. This is also essentially the motivation that appeared in Davide's talk this morning. The idea is that if we look at in field theories, we can get much richer structures by including more complicated things. So in the formalism of extended field theory, we might try to assign things to higher codimension manifolds, not just the top in codimension 1. More physically, we can look at OPE algebras, algebras made of local operators. We might get categories made out of branes. We might get higher categories made by studying various defect operators. So for some example, I don't want to talk very formally about what an extended topological field theory is, but just here's some kind of physical examples. If we look in a two-dimensional field theory, we have boundary conditions in topological field theory. That these are D-branes in examples of A or B models, A or B branes. That's an example of a category that we attach to something in codimension 2. Another example of a category in codimension 2, which is also the subject of Dan Fried's talks, was the line operators, the Wilson loop operators, for example, in Chern-Simons theory. That's a category that we can think of as attached to the circle in a three-dimensional topological field theory. Similarly, if you look at line operators in a four-dimensional topological field theory, the Wilson-Raytoft operators, for example, in n equals 4 super Yang-Mills, this gives an interesting example of a category which you can think of as attached to the link of your line operator, which is a two-sphere. Or you can look at a two-category of surface operators in a four-dimensional field theory. So none of this will be needed. This is just sort of to motivate that we get more and more complicated, richer structures from a topological field theory by looking at various singularities and defects and higher codimension operators. And the main point about this is that any of these things we get, so we get algebras, we get categories, we get higher categories, we get various more and more elaborate structures. But whatever we assign to any manifold in any topological field theory will always be finite dimensional, quote unquote. It will always be dualizable in the sense that you can always take your manifold. This had a nice red color here, but take your manifold and you write your left elbow, you write your right elbow. You have the exact same diagrams. And you can take that as an axiom of what you mean by finite dimensional. It's something that has an evaluation map, a co-evaluation map, an evaluation map that satisfy this mark of Zorro. And that gives us, in particular, a notion of a dimension. So any of these things we find in field theory has a notion of a dimension. I'm just going to use the word dim. The dimension of what the field theory assigns to n is what the field theory assigns to n cross S1. That's it. It's not. You can say this mathematically in terms of, well, you take the unit, you apply the co-evaluation, then you apply evaluation, you see what you get. So that gives you a mathematical definition of the dimension of a dualizable object. So it's basically just compactifying a theory on an additional circle, which we know very familiar with. This is an operation of taking a trace. So it's the same thing we're very familiar with is in physics.
So it lands you not in numbers necessarily, but vector spaces or categories or whatever.
Yes.
Okay, you just uncovered that.
Tricky. That's right. So the idea is that what I'm calling dimension is not a number, as Jacques said. It's something. It's decategorification. Whatever you started, it drops you down one level of structure. You started with a vector space, you got a number. Started with a category, you get a vector space. You start with a two category, you get a category, and so on. So the mathematical, the words to say at this point are the theory of Hochschild homology. So there's a notion of Hochschild homology for dualizable objects in various higher symmetric monoidal categories. And I'm going to suppress that language as much as I can. But so hopefully there's some intuitive idea here of what do I mean by this dimension. And here in some invisible color, one thing that's also important in this theory is what's the analog of cyclic homology, is the fact that we had a circle. So you can ask what happens when you rotate the circle. So this dimension has an extra structure, which is what cyclic theory is about. And I'm mostly going to, so that's an important part of the story that I'll mostly suppress. So, OK, so we have this notion of dimension in a field theory. And you can ask, what could you possibly prove about these things in this kind of generality? I mean, it's sort of lacking in much structure. There's something very formal you could say, which is that the notion of dimension is preserved under domain walls. So if I have one field theory, here's my original field theory Z. I have another field theory W, and I have some kind of notion of passing between theory W and theory Z. I have some kind of boundary between the W theory and the Z theory. And the notion of dimension wall, I can think of that as just mathematically just a map from W of M to Z of M. So for any particular manifold M that I'm going to study the theory on, I look at W of that M, and there were nice colors here. I'm sorry. This has one color, and this is another color, and there's a little dot in between. Yeah, sorry, that's not very well. All right, I'll draw it if you ask. OK, so the point is that if I give you such a map, whatever W of M is, and Z of M is something of the same kind, and there's a domain wall, there's a boundary between the W theory and the M theory, then you can just cross with an additional circle, and you get a map from the dimension of W of M to the dimension of Z of M. The same wall in my theory gives me a way to go from the dimension to this dimension. Now, we say if dimensions are numbers, it's not very interesting to talk about maps between numbers. But if the dimensions are vector spaces, this is going to be a map between some Hochschild homology vector space and some other vector space here. And so, for the most, maybe most useful example of a domain wall is a boundary condition. So if you look at if you have a domain wall with a trivial theory, you just have the theory Z, and you have a way of just putting a boundary on it. Then that's, if you'd like, that's giving me a vector, an element of Z of M. It's whatever I assign to this empty set, giving me something in Z of M. So that gives me what you might call the boundary state. I have a boundary condition, an element of Z of M. It gives me a boundary state, which is an element of dim Z of M. This is a way to formalize boundary states in this theory. So this is sort of not, doesn't really sound like a theorem. Let's just say it a little more mathematically, that if you're in some context, you talk about dualizable or technically right dualizable morphisms of dualizable objects in some settings. So you have two things, C and D, which have this kind of dualizability properties, and you have a nice kind of map between them. Then you can take its dim, and you get a map from dim of this guy to dim of this guy. So technically, this dim is a symmetric monoidal functor on dualizable objects and right dualizable morphisms. This is just saying you can compose dims, and they behave the way you think. So this is not, this is kind of a triviality, but it's, as I'll try to convince you, it's a useful triviality. So, so in particular, this gives you the notion of characters. So if I give you a boundary as my domain, well, if I have a map from the unit to C, that's a particular object of C. If I'm thinking of C as a character, it corresponds to a class in dim C. This is a special case of what's above. There's a notion of Chern character, or character of an object in C is it gives you a vector in dim C. And it satisfies functoriality. So now all of this is a special case of this amazing theorem that I think needs more advertisement is the cobordism hypothesis with singularities of Jacob Lurie, which is sort of buried in his document on the cobordism hypothesis, which is it helps you understand the structure not just of topological field theories, but of arbitrary kind of defects and domain walls and higher, kind of more elaborate structures in field theory in a formal way. Now, while we're definitely using a lot of Jacob's foundations, we don't actually, to prove this, you don't need any of this fanciness. This is something you can just write down directly, whatever, this kind of functoriality. But in any case, this is sort of the natural context in which to think of this. OK, so that's kind of the abstract nonsense overview. So I wanted to talk about how you apply such a thing in some, to get some interesting geometric content. So my talk is going to be structured. I want to talk about two-dimensional field theories, three-dimensional field theories, and when I'm out of time, about four-dimensional field theories. So let's start with kind of the most familiar context. I'm going to talk about B-model type things. What do I mean by B-model type thing? I'm going to take X to be any algebraic, complex algebraic variety. And I can look at a category, the derived category of quasi-coherent sheaves, or B-branes on X. So to any algebraic variety, I can assign a category. the category of just complexes of finite complexes of vector bundles, for example, on X. I'm calling this a B-type theory because to actually get the B model, to get a full topological field theory, you need X to be smooth and compact. And if you want really no framing and all, you need a Calabi-Yau. But for the kind of things I'm going to be talking about, I just take X to be anything. But I think it's good to think about it as a B model. And so in the B model, we know what to assign to the circle. So the idea, and this is what we assign to the B model on a point, is this derived category of quasi-coherent sheaves. B model on a circle is somewhere here. Yeah, so the dimension of this, by my general formula, the dimension is what you assign to a circle, which is the Hochschild homology of X, which is just the cohomology of the differential forms. This is just the Dolbeault cohomology of X. So the dimension of the derived category of coherent sheaves is just the Dolbeault cohomology of my variety. So that's a very familiar thing. If you wanted to make Durham cohomology, you naturally should look at cyclic. But again, I've said I'm not going to say cyclic. So that's sort of a natural refinement. And this notion of character that we're talking about is just a familiar Chern character. If you give me a vector bundle and a variety, you think of it as an object here. It has a class by this formalism in the dimension of the derived category, which is Dolbeault cohomology or Durham cohomology. And that's the Chern character, or if you'd like, the D-brane charge. OK, so that's what this theory of characters is. It's just usual Chern characters. And now what we can get out of this is that there's a functoriality that we talked about, this general principle that you can pass through domain walls. Well, what are domain walls in the B model? If you give me, for example, a map between varieties, more generally, you can use some correspondence. But if you give me a map of varieties which is proper, or some more general domain wall, which just means a continuous functor of these derived categories, then you get a map on Hochschild homology. So a map of varieties gives a map on the proper map on varieties gives a map on Hochschild homologies. That's functorial. So what you get out of this functoriality, you get, for example, if I give me a vector bundle on X, I can push it forward to Y. And what we get is a compatibility between taking the push forward of the vector bundle. If you take the class of the push forward of the vector bundle, that's the same as taking the Chern character of my vector bundle and then applying this functoriality, dim f star. So this is basically a Gortendieck-Riemann-Roch theorem, or in the case of a point, this is Hirzebruch-Riemann-Roch, except you'll notice there are no Todd genuses or anything. This is because I'm working really in Hochschild homology. The Todd genus comes if I want to make the comparison with usual Durham cohomology. And this story, in the case of smooth proper varieties, was worked out in a series of very beautiful papers. Markarian, Calderaru, and Calderaru-Willerton, Ramados, and Shkliarov have explained this story very, very beautifully. OK, so any questions so far? All right, so now what I'd like to do is let's look at gauge theory. And I'm going to I'm talking topological field theory, so these are some kind of topological gauge theories. So here I'm going to take my group G to be a semi-simple, complex semi-simple Lie group, or more generally, if you like, an affine algebraic group. And I look at this category. I can assign a category to a group, which is just the category of representations of the group. That's the natural category you'll think of if you have a group. And again, I have the similar kind of analog of the smooth and proper I had before. If G is, for example, a finite group, then you get a full two-dimensional topological field theory out of this construction, and that's basically Dijkgraaf-Toy version, easier version of the Toy version of Dijkgraaf-Witten theory. So this is kind of a silly version of kind of topological Yang-Mills theory. But I'm allowing here G to be a general complex semi-simple group. You get something more interesting. So what is the dimension of this category? Well, we know it's supposed to be just what the gauge theory assigns to the circle. So gauge fields on the circle are just, I'm using this funny notation, G over G, to mean the adjoint quotient, G acting on itself by conjugation. And so we just get class functions. What this field theory assigns to the circle is just class functions on the group, algebraic class functions if your group is not finite. And so that's what the dimension of categories of representations are. And what is the notion of character? It's just the notion of character. If I give you a representation of a group has a character, which is a class function. Here, V is a finite dimensional representation. It has a perfectly nice character, which is a class function. So particularly, you notice the Chern character and character of a representation are the same same thing. So we can think of this as really being the same example as we had before, except we can think of this gauge theory. Maybe this makes physicists unhappy to think of gauge theory as a kind of a sigma model into a classifying space. But just formally, that's all we're doing. You can think of this as a kind of B model with target. Well, if the G is finite, it's an orbifold. In general, there's a stack, which is just a point with symmetries G. And that's all we're doing is exactly what you would think if we ask what is the B model on point with symmetries G. Well, you look to the point, the B branes are just vector bundles, and to the circle, you're getting functions you're getting the Hochschild homology, which here is just class functions. So it's the same thing we did before, just in an orbifold or stacky context. So you say that, you're like, well, why not have just a general orbifold, a general stack? Let's have some more interesting examples. So let's, you can say for a general stack, but let's be a little more concrete. Let's take your favorite variety with a group action, and let's take the quotient. But I mean the quotient now as an orbifold, or as a stack. In other words, I'm going to remember stabilizers. So this is, in this case, let me introduce some version of, this is what you might call the B model version of the loop space. It's the part of the loop space that the B model sees. And this actually appeared in Miranda's talk this morning. So you look at let me call it, it's usually called the inertia stack, or inertia orbifold. You take points x in x, elements G of the group, such that G is in the stabilizer of x. So you look at these pairs. The group G acts on these pairs. And I'm going to call this the loop space of x, or the inertia. So it can be interpreted as a loop space. In some sense, I'm just not allowing loops that kind of go all the way around my variety. The only loops I'm looking at are kind of loops that wrap around an automorphism, that wrap around stabilizers. Sort of loops without instanton corrections in some sense. So for example, if my orbifold is point mod G, then loops just means, well, I have a point in x, that's just the point, and automorphism is an element of G up to the symmetry, that's just what we had before, G mod G. So this G mod G is an example of this loop space. And then you can prove a theorem, it's sort of almost definitional. Well, anyway, there's an easy theorem to prove that the dimension of this derived category of this x mod G is Dolbeau cohomology of the loop space. So this is a theorem that kind of combines the point mod G version, the pure gauge theory, and the B model. So if you'd like, there's some kind of, we're looking at some kind of gauged B model, a gauge sigma model into X, and we're reducing it on the circle, and this is the vector space we get. So it contains all of the twisted sectors. This G mod, you see that you get exactly all the twisted sectors. That's what this loop space does. So this is some version of orbifold cohomology, except again, I don't need my group G to be finite. So that's this Hochschild homology, or this dimension is where the natural home for where characters of B-branes, or vector bundles, on the stack live. So that's a calculation. And so now you can ask, what about functoriality? What does this kind of functoriality or Riemann-Roch theorem tell me in this context? So what's an interesting map to apply functoriality to? Let me take the stupidest map we know, which is take x to map to a point. You have map x to a point. So this is a map that's G equivariant, where G is acting on x the way it acts on x, and acts on point the way it knows how. So that means you can take the quotient by G. I can think of a G equivalent map equivalently as a map from X kind of gauged by G to points with G symmetries. I'll call that map pi. And you can think of this if maybe, I don't know if I'm abusing physics language that I don't really understand, but I think of this as a kind of a domain wall between the gauge sigma model and the pure gauge theory, where I'm integrating out the sigma model, the fields in X, and getting just the pure. Anyway, if that's really the wrong thing to say, I'm sorry. Anyway, so we have this map in any case, whatever you call it. And in particular, you can look at loops. You have a map from x mod G to point mod G. Look at loops into that map, loops into pi. So that's a map from the inertia to G mod G. So the inertia stack canonically maps to G mod G. Now, what is this map? It's something very obvious. It's just a collection of all the fixed point data. So if I give you a group element, so you're just looking at pairs x comma g, and you send them to the conjugacy class of g. So in other words, the fiber over a particular conjugacy class is just the fixed point set of that particular group element, modulo its symmetries. So this map is just collecting all of the fixed point data in X in a nice way. So I like this as just as a way of organizing fixed points. It's probably very common in some other language or other. So now all this theorem, now you take the exact same abstract nonsense functoriality, and you just work out what does it give you in this setting. It gives you something very concrete. It gives you that the map, we know that we have this dim map. You look at the derived category of x mod g, and you have the derived category of point mod g, in other words, representations of g. So we know we have we have a map between the dim of this and dim of that. And the claim is that map is just integration along L pi. That's all it is. That just follows from the definitions. So in order to calculate this functoriality, they're realized very geometrically by the fixed points. So in other words, push forward on Hochschild homology is just given by integration along this map. In other words, it collects all the fixed points data. So as I said, this is just working out what this general formalism gives you in this case. So what is this saying? This is something that's very familiar in maybe under more restricted hypotheses. This is the version of the Theobot fixed point theorem. So you're saying that suppose I give you an equivariant vector bundle on X. That's what it means to have a vector bundle on X mod G. It just means equivariant vector bundle on X. Now what is this push forward? Push forward to point mod G. We're getting a representation. That's just the representation, which is the global cohomology of V. So to a vector bundle, we push it forward. We get cohomology of V considered as a G representation. And now what we're asking, what about characters? You take the character, so dim pi star V, that's the character of the representation on cohomology. And so what is this theorem telling you? It's telling you that the dimension of this, so this character can be identified as integration of the Chern character of V along this map. In other words, if you want to evaluate the character, you want to take the trace, alternating trace of G on cohomologies of a representation, it's given formally completely by the fixed points xg. It's an integral over the fixed point. So that's the Theobot fixed point theorem, except that there's kind of no assumptions here. You need the map to be proper. So you need X to be proper. That's what tells you X mod G is proper over point mod G. So say X is projective. But you don't need any kind of transversality or isolated fixed points. This works in families, for orbifolds, for affine algebraic groups, and so on. OK, so you get a version of a Theobot very easily from this formalism. Now, what do I mean by Theobot? This is a Theobot for Dolbeau operators. It's a Theobot is, I guess, about an elliptic operator. Here, it's a Theobot for Dolbeau operators for holomorphic cohomology. You can tweak this pretty easily to talk about Durham operators, if you prefer. So you go from B model. A model is too hard for us, but there's a kind of a toy version of the A model. A model on the cotangent bundle, which is mathematically we just take a Kapustin with an ansatz and call that D modules. So now it's a curly D. There's this notion of category of D modules. D module just means a quasi-coherent sheaf with a flat connection. So it's just a vector, like a vector bundle with flat connection, just you allow some singularities. And more physically, you can take the cotangent bundle of X and deformation quantize it and think of B-branes there. And then you can you can interpret this as a certain kind of A-branes on T star X. OK, so you can now take this field theory and do everything the same as we did before. I mean, this is abstract nonsense. It applies in all these sittings. The only thing you need to calculate is what is dim of D modules. So dim of this category. And the point is, it's the Durham cohomology now of the loop space. So before it was Dolbeau cohomology of the loop space. Now you calculate that it's the Durham. This is with Nadler. We proved it's, again, pretty easy that it's the Durham cohomology of the loop space. And so for example, one thing to note is if X is a variety, there's no loop space. There's no automorphisms. So this just means the Durham cohomology of X. If you have a free action, if there are no stabilizers, this is just Durham cohomology of X. But this is a little smarter. It keeps track of twisted sectors. OK, and so this tells you if I give you a G equivariant flat vector bundle now, so kind of a Theorem operator, it has a turn class, which is really a cohomology class of this loop space. So a cohomology class with twisted sectors. And now you apply this functoriality theorem, and you get an Inertia bot theorem for Theorem operators. So let's do an example. This is sort of the classic example where let's the group just be Z. So let's just take a single diffeomorphism, single automorphism of my variety X. You just have an automorphism. I don't mean autoequivalence, just automorphism of X. So the way I've been setting it up, I mod out by the action of this automorphism. That's just a silly way of keeping track of this data. I think of X mod this automorphism mapping to point mod Z. And then you take the constant, say, for example, take the constant sheaf. That's a nice flat vector bundle. Its push forward just means take the cohomology of X. So I'm just taking the Theorem cohomology of X and thinking of that as with the action of gamma. So gamma gives an operator on the Theorem cohomology. And this dim is now just this super trace, just alternate sum of traces of gamma on the cohomology. So that's what I'm calculating. And if you look what we're doing now, there's only kind of one interesting point in G mod G, which is gamma. The fiber over it is the fixed point set. And so you're just saying that the trace of gamma on cohomology is calculated in terms of the fixed point, and that's the Lefschetz fixed point formula. OK. So these are kind of examples. How much time do I have? 12? OK, it's a complicated calculation. OK, so now what I'd like to do is talk about how this applies in representation theory, which is sort of our motivation. So I'd like to go to three-dimensional gauge theory, but before that, let me do some example of what I just did. So I'm going to start with an example of this Inertia bot story in the case where my X is already a homogeneous space. So look at X as G mod K, your favorite group and favorite subgroup, as a homogeneous space. And so I'm going to take as my vector bundle, say, for example, take the trivial vector bundle. That's certainly a nice G equivariant vector bundle. And if you look at its push forward, that's functions or some higher cohomologies on G mod K. This is what you call the induced representation from K to G. So for example, I think for this slide I initially had, might as well think of G and K being finite. And then you're taking a finite group, taking a subgroup, looking at functions on the cosets, and that's induced representation from K to G. And so you ask, how do you calculate the character of an induced representation? That's due to Frobenius for finite groups. Well, we just apply this geometric machinery, just work out what it tells us. So loops into X mod G. Well, X is G mod K. What is this inertia thing? It's a point in X in G mod K together with an element of its stabilizer up to the action of G. That's our LX thingy. In this case, well, G is acting transitively, so we're really looking at loops into point mod K. So if I take G mod K mod G, I get rid of all the G's. So it's loops into point mod K, so that's really K mod K. So I'm looking at the map from K mod K to G mod G coming from the inclusion, the map from K to G. Or if you'd like, more concretely, giving such pairs, you could just forget about X and remember G. Okay? So it's a very nice map. And so now you take the Chern character of the trivial vector bundle. That's a function on this loop space. It's the constant function 1. And so the claim is then that the character of the induced representation is the push forward. It's just the integral over this map of the constant function 1. Or in other words, it's just, well, for finite groups, this is just a finite sum. You're just counting how many ways to take a conjugacy class in G and represent it as a conjugacy class in K. So just summing over the fibers of this map from K mod K to G mod G. So that's the Frobenius character formula. That's what the character of an induced representation is. An example of this is one of the original applications of a Inertia bot, is the Weil character formula. And so what is the Weil character formula? Now we take X to be G mod B. So G is now my complex Lie group. B is the Borel subgroup. G mod B means the space of flags in Cn, if your group is GLN. This is the flag manifold. And now you apply this, and you get a very famous map in representation theory called the Grothendieck-Springer simultaneous resolution. It's the same map we've been talking about all along. It's this map from loops into X mod G to G mod G. And it's a simple thing. It's just you take a group element, and you take a point in G mod B, in other words, a flag in Cn, if you're GLN. Take a group element and a flag that it preserves. That's what our inertia is, up to simultaneous action. And then forget about the flag. Just remember the group element. So this thing is called the Grothendieck-Springer resolution. It's an amazingly beautiful thing, and sort of shocking how much of representation theory boils down to the study of this map. For example, if you look at unipotent elements in the group, this map basically looks like the moment map from the cotangent bundle of G mod B to the nilpotent cone, which is a very beautiful resolution of this very complicated singular variety. We won't need much of that. So this map gets very interesting and complicated if you look at complicated elements in the group. But if you take your favorite element with distinct eigenvalues, take a group element that has all distinct eigenvalues, so regular semi-simple element, then you're just asking how many flags are preserved by a regular semi-simple element, and that just means permuting the eigenspaces. That's the only way you're going to make a flag that's preserved by something with distinct eigenvalues. And so you find there's n factorial fixed points, or in general, the order of the Weyl group. So every regular semi-simple element gives you just n factorial fixed points. So this map is actually a Weyl group kind of covering space, Weyl group Galois cover that's over the nice set of regular semi-simple elements. And that's all you need for the Weyl character formula. You end up not caring about all these complicated elements. You have a holomorphic function, and it's determined by what it does on these nice elements. So you get, as a result, the Weyl character formula. You take as your equivariant bundle, you take your line bundle, holomorphic line bundle on the flag manifold. Those are labeled by highest weights, by the weights for the group G. And you look at the representation on the holomorphic sections or holomorphic cohomology of this. And the formula we just talked about, exact same formula, tells you that the character of this representation is given explicitly as a direct sum over fixed points, so it's sum over the Weyl group. So this is the familiar Weyl character formula. OK, so now what I'd like to do is go to a kind of less familiar setting, which is three-dimensional topological gauge theory. So there's a particular gauge theory I'm going to talk about, which David Nadler and I introduced mathematically in a paper. We call it the character theory of a complex group. Witten explained that this is a particular special topological twist of maximally supersymmetric Yang-Mills in 3 dimensions. But anyway, this is the context in which we want to apply this, but let me just tell you what kind of things are going on in this theory. So when you're looking at 3-dimensional gauge theories rather than 2-dimensional gauge theories, what you find is that if you're trying to study on what happens on the level of a point, or kind of the worst defects you can introduce, you're replacing representations of the group, so vector spaces with a G symmetry, by categories with a G symmetry. So everything gets categorified, and we're looking at your group acting on some kind of categories. And now you have to say what kind of actions. What do you mean by group action on a category? And there are lots of different versions. I'm going to look at what you might call flat actions, where the matrix elements of this action are vector bundles with flat connection on the group. So it's a particular class of what do you mean by saying what is the group acting on a category. There are many. You can do this with other versions, but that's the case that comes up in this particular field theory. So you ask, what do I mean? Where do you get group actions on categories? How does that look? Well, if a group acts on a variety, and you look at some natural category attached to it, like the category of these flat vector bundles or D modules, then the group will act on this category. So if you look at D modules on X, then the group will act in the way that I like. That's a natural example of representations of the group on categories.
What does the adjective flat mean?
Flat just meant that what does it mean for a group to act? How do you specify a nice class of actions of a group? You have to specify what do you mean by the group algebra. So do you take L2 functions or compact, L1 function, I guess, compactly supported continuous functions? You have to specify a class of a group algebra, and that'll tell you what you mean by representation. When you go one level up, when you say group algebra, you mean some kind of sheaves on the group instead of functions on the group. And you have to specify what kind of, that's what I meant by this matrix element comment. You have to specify what kind of sheaves on the group are you. So now the claim is the dimension of this guy is, well, you integrate the constant function. You take, well, now constant function became the constant sheaf. So the dimension of the induced representation is the integral of the constant function. You take the constant sheaf on this space X mod G, and you push it forward. This is something that's very familiar to representation theory. It's called the Springer sheaf. Just means it's a collection of all the cohomologies of these fixed point sets. It's a sheaf that keeps track of all of these cohomologies. But this sheaf goes much, much further back. Historically, it's something that's known as the Harish-Chandra system. What do I mean by system? Well, these D modules, these are really can be interpreted as systems of linear PDE. So this is a particular system of linear PDE on the group. And this is exactly the system of linear PDE that Harish-Chandra studied. So Harish-Chandra was studying infinite dimensional representations of real Lie groups. And he was trying to define what you mean by character. for one of these, say, principal series, unitary representations of a group. What he said, well, it's going to be some kind of, he showed you there's a distribution on the group, but this distribution is actually incredibly well behaved because it satisfies a really strong, maximally overdetermined system of differential equations. This is the system. And so it just means you set the Casimirs to some numbers. But anyway, this is how Harish-Chandra proved that developed the character theory for these infinite-dimensional representations. You actually get basic analytic functions on the group rather than with some controllable singularities. So how does the theorem I just stated relate? Yes. Oh, 5. Oh. All right. So how does the theorem I stated relate to this? Well, we said that this Harish-Chandra system is the character of D modules on G mod B. OK, what do you do with that? Well, there's a beautiful theorem of Valence and Bernstein that says that if you look at these D modules on G mod B, which a priori you would say, why do I care about them? Valence and Bernstein tells you that D modules on the flag manifold are the same thing as representations of the Lie algebra. Or if you're interested in Harish-Chandra modules, the kind of representations Harish-Chandra studied, you can put them as particular kinds of objects here. So the entire Harish-Chandra theory of these admissible representations of Lie groups sits inside of here. They're particularly nice objects in D modules on G mod B. So this thing, this induced representation, is something that you care about in representation theory very classically. And so now you can combine this, and you say, well, this is in sort of ongoing work. You can now say that given a nice Harish-Chandra representation, you think of it as an object in D of G mod B, it gets a Chern character, which is now a section of the character of D of G mod B. We've kind of gone enough levels that you have kind of characters inside characters. The whole category has a character, which is this Harish-Chandra system, and the particular object has a character, which is a solution of the Harish-Chandra system, roughly speaking. And so you recover. Well, this is still something we're working out the details, but what we expect is to recover this kind of Harish-Chandra theory of characters, and in particular the kind of analogs of the character formula, which were Harish-Chandra proved in some cases and Schmidt and Villonen proved very general cases, and it should follow from the picture I said before. That's something we're working out now. And so now in the last 3 minutes or some number of minutes, I just wanted to quickly say some words about four-dimensional gauge theory, which is sort of the real motivation for a lot of this. So here we're now going to a four-dimensional gauge theory, which is twisted n equals 4 super Yang-Mills in 4 dimensions. Geometric Langlands program is, as Kapustin Witten explained, is a small part of the study of this theory. In particular, we're going to fix a Riemann surface, sigma, and I'm going to look at category D modules on the space of G bundles on sigma. Did I give the translation yet? Yeah. So translation, we're looking a branes on the Hitchin space of sigma. We're looking at the Hitchin space associated to sigma, and we're interested in the category of a branes. We're looking in this, we reduce on sigma, we get an A model field theory on this Hitchin space. And so we're interested in studying the category of D branes there. And that Geometric Langlands program is all about studying this category. So what can you ask about the category in this language? Well, the first thing you can say is, what is its dimension? You have a category, what is its dimension? Or mathematically, this is, what is its Hochschild homology? So what is its dimension? Well, actually, this follows from a theorem I had in some previous slide. Its dimension is the Ramp cohomology of its loop space, of its inertia. OK, so in other words, you're asking, what is this topological field theory assigned to sigma cross a circle? What it assigns to sigma cross a circle is this vector space, which is the Ramp cohomology of this inertia of Bungie. Now you ask, what is inertia of Bungie? Well, it's something very familiar. It's a space of Higgs bundles. Or more precisely, it's a group-like version of the Hitchin space. So I look at a G bundle together with, rather than an endomorphism, I look at an automorphism. And I can twist it to allow arbitrary poles. But let's ignore that. So anyway, you have a G bundle with an automorphism. So it's basically the Higgs. That's why I'm capitalizing the Higgs. It's basically this. So the point is that the space of Higgs bundle on sigma has this different role. Has nothing to do here with a cotangent bundle. Has to do with inertia. The inertia of Bungie is this Higgs space. And so it follows that, so the cohomology of the Hitchin space is the dimension. So now where does this come up? Well, this is sort of the central object in Ngo's work on the fundamental lemma. So I'm ignoring group versus Lie algebra distinction. But Ngo says that reduces the proof of fundamental lemma to geometric properties about the cohomology of this space. And so this now makes a little more sense. Well, he's trying to prove the fundamental lemma, which is part of this Selberg trace formula. He interprets it geometrically, and what I'm trying to claim here is that this cohomology is a dimension. It is a trace in a natural way. And so this, or let me, just to be a little more precise, what Ngo actually does is he doesn't look just at the total Hitchin space, he looks at the Hitchin fibration. That's everyone's favorite thing to do with this space. If you have a Higgs bundle, you can attach it to a spectral curve. There's this Hitchin's completely integrable system. And what Ngo does is he studies the cohomology of the fibers. So not just the cohomology of the total space, but you get a sheaf on the space of spectral curves, which is the cohomology of all the different fibers. That is the thing that Ngo studies. And now sort of the punchline here is that this sheaf is the character. It is the dimension of D modules on Bungie, but not just as a plain old category. That's kind of boring. It's not just a plain old category. It has lots and lots of symmetries. It has the Etofta loop operators, or the Hecke operators. This category is a module over a huge algebra of symmetries. And you want to identify, this is the natural version of the trace formula, the Arthur trace formula in the geometric setting. What is the character of this representation of the Hecke algebra? And the point is that you can now define, so there are interesting kind of geometric things in defining. There's some things infinities to regularize to make sense of this, just like in Arthur's version of the trace formula. And they have nice geometric interpretation. But in any case, you can now see all the geometric ingredients of Ngo's thing as really part of a geometric version of the trace formula, which we're now trying to develop. Thank you.
Questions?
Why is it a Higgs bundle but not a Higgs type bundle? Is it a Higgs bundle?
What is the Higgs?
The automorphism of the Bungie.
Yeah.
Is it always a Higgs bundle or is it a Higgs type bundle?
Higgs what?
Higgs type bundle. Like where is the?
I'm not sure what that means. I just mean, so I literally mean it's a G bundle together with an automorphism. And if you fix a level structure, it's an automorphism with some fixed divisor of poles. So I'm not twisting by the cotangent bundle like you usually do. Yeah, it has nothing to do with the cotangent bundle of the Hitchin space. That's sort of a confusing thing when it goes through. It came out, it was like, you might think that the immediate weight related to Langlands or to physics is as a cotangent. The cotangent bundle has no role here. There's a different role for Higgs bundles as this inertia, as this loop space of the Hitchin space. And that's really what's okay. So there's no, it's not symplectic. And when I say Hitchin integrable system, I don't mean it's not, not an integrable system, but they're still the same map. The Higgs bundle can have an automorphism, you can still attach it to the spectral curve. And that's really what appears in, that's what you're interested in studying.
Questions? Not, let's thank you. Start again at 5 after.